Hey everyone, and welcome to The Explainer. I am absolutely pumped to have you here today. We are going to explore the foundational physical rules of how our world actually operates. We're going to take a really mind-bending look at everyday concepts, things you probably thought you already understood perfectly, like work and energy, and we're going to break them down to their absolute scientific core. By the end of this, I promise you, you're going to look at every movement, every lifted box, and every speeding car in a completely new light. Let's get into it. Here's our roadmap for today. First, the physics of work. Next, we'll introduce time to understand power. Then, we look at potential and kinetic energy, connect them with the work-energy theorem, and finally, wrap the whole thing up with the grand synthesis of energy conservation.
Section 1. The Physics of Work. Redefining Everyday Exertion.
Okay, let's dive into this because we actually need to completely redefine a word that you use every single day. I want you to really picture this. Imagine you're pushing a massive, solid brick wall. You're pushing with all your might. Your muscles are absolutely burning and you're sweating profusely. The question is, are you doing work? Well, in everyday conversation, absolutely you are. But in physics?
The crazy answer is no. Imagine someone pushing a car, and because they're pushing, the car is actually rolling forward. Now contrast that with someone straining against that completely stationary brick wall. Despite all the physical exertion, all the sweating and grunting, pushing that wall results in zero scientific work. Why? Because there is absolutely no displacement. The wall didn't move. So no matter how exhausted you feel, scientifically speaking, zero work was done on that wall. But the moving car, because it actually moved in the direction of the push, work definitely happened there.
And here's the core reason why. The strict scientific definition of work demands two distinct things. A force absolutely must be applied, and there must be a physical displacement of the body. You just multiply the force by the displacement to calculate it. We measure this resulting work in a unit called joules. If either the force is zero or the displacement is zero, the mathematical product is just zero. No movement, no work, period. Now, what's really wild here is how the exact angle between your force and the displacement completely changes the outcome. It's governed by the cosine of that angle. If they are pointing in the exact same direction, boom, you do positive work. If they oppose each other, think about friction, dragging against a sliding box, that's actually negative work. But check this out, the 90-degree scenario. If you carry a really heavy box on your head and just walk horizontally across a totally flat floor, the downward force of gravity and your horizontal forward movement are perfectly perpendicular. The cosine of 90 degrees is zero, which means technically against gravity, you are doing zero work. Kind of blows your mind, right? Section 2. Power, the rate of work. Introducing the critical element of time. So, what happens when we're suddenly on the clock? What if we care about how fast that transaction of work actually gets done? This introduces a critical new element, time. And this is exactly where power comes into play. Power is just the rate of doing work. You simply take the total work done and you divide it by the time it took to pull it off. It's measured in watts, or in bigger everyday contexts, kilowatts, megawatts, or even horsepower. Basically, a machine that can do the exact same amount of work, but in half the time, that machine is twice as powerful. So the crucial point here is that work only cares about the final result, right? If you carry a heavy box up a flight of stairs in 10 seconds, or if you take 10 whole years to carry that exact same box up those exact same stairs, the scientific work done is identically the same. But power. Power cares deeply about the clock. Doing that job in 10 seconds requires vastly more power. Section 3. Energy, potential, and kinetic. The universal currency. Now, if work is a physical transaction, what's the actual money being used to pay for it? You can't just do work for free. We need to talk about energy, which is literally the universal currency of our physical world. Energy is simply defined as the capacity of a body to do work. And just like work, we measure it in joules. In mechanics, we're generally dealing with two overarching forms. Potential energy, which is stored energy based on an object's position or state of rest. Think of a massive amount of water held back high up behind a dam. And then there's kinetic energy, which is the vibrant, active energy of motion. Let's trace how this builds into one of the most famous equations out there. How do we actually measure kinetic energy? Well, a really clever way is to calculate the exact amount of work it takes to force a moving object to a dead stop. We already know force equals mass times acceleration.
Using some basic equations of motion, we figure out the stopping distance. And when we multiply that stopping force by that stopping distance, remember, work equals force times displacement, the math beautifully and elegantly simplifies right down to exactly 1/2 mass times velocity squared. That right there is the literal mathematical currency of motion.
Section 4. The work-energy theorem, connecting the transaction to the currency. All right, we have finally arrived at the grand synthesis. We're going to connect the transaction, which is work, directly to the currency, which is energy. This is known as the work-energy theorem. It states that the work done by a force acting on a moving body in its direction of motion is exactly equal to the increase in that body's kinetic energy. If you push a moving shopping cart and you do 50 joules of work on it, you have quite literally deposited 50 joules of kinetic energy straight into that cart's account. It speeds up accordingly. It is a completely perfect one-to-one transfer. Section 5. Transforming and conserving energy. The grand synthesis. So, we've seen how work deposits energy into an object. But how does this energy move around the broader physical world? How does it actually change states? Because the mechanical energy of pushing cars and carrying boxes is really just the beginning. Nature provides us with an unbelievable diversity of energy forms. We've got solar energy radiating down from the sun, the chemical energy literally stored in the food we eat and the fuels we burn, electrical energy, nuclear energy, right down to the actual sound energy vibrating your eardrums at this very second. It's everywhere. And it's honestly brilliant when you realize how interconnected all these forms really are. We almost never use energy in the exact form we find it. We have to convert it. For instance, a dynamo converts mechanical energy into electrical energy. A thermocouple changes heat into electricity. A loudspeaker turns electrical signals into sound. Even something as simple as lighting a candle is taking stored chemical energy and transforming it right before your eyes into light and heat energy. Our entire modern world is basically just one massive web of energy conversion. Let's think about a super relatable physical example of this conversion in action. Picture a tightly compressed spring with a little ball resting right on top of it. In that squished, compressed state, the spring is holding on to elastic potential energy. It's just sitting there, waiting to do work. But the millisecond it's released, that stored potential energy is instantly transformed into the active kinetic energy of the spring uncoiling. It does work on the ball, transferring that kinetic energy and launching it flying straight into the air.
Now, all of these wild conversions are governed by one unbreakable universal law, the principle of conservation of energy. It states simply, energy can neither be created nor destroyed. It only ever changes from one form to another. If you drop a ball off a roof, its potential energy steadily decreases, but its kinetic energy increases by the exact same amount as it speeds up. In a closed system, the total energy account never, ever changes its balance. So I want to leave you with this final, kind of provocative thought. If energy is completely conserved, if it's literally impossible to lose or destroy it, why on earth do we constantly worry about an impending energy crisis? Well, the answer lies in the concept of degraded energy. When we transform energy from one state to another, a part of it inevitably turns into forms we can't easily capture or use anymore, like ambient heat just dissipating into the surrounding air due to friction. The total amount of energy in the universe is exactly the same, but its usefulness to us, that's been spent. It's a really fascinating paradox to ponder the next time you look at the moving, working world around you. Thank you so much for joining me on this explainer, and keep questioning the mechanics of reality.